When you think about it, what's the real line between you and, well, everything else? At the most basic biological level, it's this: the cell membrane. And don't picture some simple wall. Oh no. This is a smart, dynamic, living border. It's constantly deciding who gets in, who stays out, and how your cells talk to each other. It's the bouncer, the communicator, and the gatekeeper of life itself. So, here's our game plan. First, we'll tackle the big picture, what this living border is all about. Then we're going to meet the actual building blocks. After that, we'll dive into all the different jobs it has. Then we'll get into this amazing balancing act called fluidity. And finally, we'll see how its structure is the key to, well, everything. Let's do it. All right, section 1, the cell's living border. To really wrap our heads around what the membrane is, we need to start with one single, core idea that just explains almost everything about it. And that big idea is the fluid mosaic model. Let's just break that down for a second. Fluid, right? That's because it's not some stiff, rigid wall. It's much more like the surface of a bubble, always shifting and moving. And mosaic because it's made up of all these different little pieces, lipids, proteins, all floating around together in this oily sea. It is a living, moving barrier. Okay, so job number 1 for this fluid mosaic is to act as a border guard. Its whole purpose is to separate the watery world inside the cell from the watery world outside the cell. And believe me, these two environments are totally different, chemically speaking. The membrane's job is to keep that delicate balance. I mean, without it, the cell just couldn't work, period. Section 2, meet the building blocks. So if the membrane is this incredible mosaic, what are the actual tiles? Let's zoom way in and meet the 3 main players that construct this amazing thing. And what is just mind-blowing is that this entire, complex, life-giving barrier is built from just 3 main types of molecules. That's it. Talk about an elegant design. So let's meet the team. First up, you've got the membrane lipids. These guys create the basic fabric of the wall. Then you have the membrane proteins. Think of these as the workers, the bouncers, the channels, the doors. And finally, there's the glycocalyx, which is basically the cell's unique ID badge. Now, the absolute foundation is this brilliantly designed molecule, the phospholipid. Just look at it. It's got a hydrophilic head, which loves water, and 2 hydrophobic tails, which hate it. So what happens when you throw a bunch of these into the watery environment inside and outside a cell? Well, they have no choice but to organize themselves. The water-loving heads face out towards the water, and the water-hating tails desperately tuck themselves away on the inside. This automatically forces them to form a perfect double layer, the famous lipid bilayer. But it's not just phospholipids in there. You've got a whole lipid family. Little cholesterol molecules are wedged in between everything, and their job is to manage stability. We're definitely coming back to that. And the tails on the phospholipids themselves can be either straight, we call that saturated, or they can have a little kink in them, which is unsaturated. Now that little bend might seem like a small detail, but trust me, it changes everything about how this membrane behaves. Okay, now for the proteins. You basically got 2 main kinds. Integral proteins are the heavy hitters. They're embedded deep, a lot of them spanning the entire width of the membrane like a tunnel. Then you have peripheral proteins. They're more like temporary contractors, just loosely attached to the inner or outer surface, ready to do a job and then move on. And finally, slathered all over the entire outer surface is the glycocalyx. It's literally a sugar coat, made of carbohydrate chains attached to the proteins and lipids underneath. But listen, this is not just for decoration. This is the cell's unique fingerprint. It's a molecular ID that tells every other cell in the body exactly who it is and what it does. Section 3, the membrane's many jobs. Okay, we've met all the parts. Now let's see what they actually do. This is where form meets function, where you see how the specific shape of every single piece gives it a critical job to perform. This chart kind of lays it all out. You can really see the division of labor here, can't you? The lipids, they form that basic boundary and they manage the flexibility. The proteins, they're the active machinery, doing all the heavy lifting, like transport and signaling. And the glycocalyx, that's the public face of the cell, managing its identity and how it talks to the outside world. And that glycocalyx ID badge is so critical. It is how your immune system tells the difference between one of your own cells and some foreign invader. It's like a secret handshake written in sugar. In fact, think about this. Your blood type? A, B, or O? What is that? It's nothing more than a different Schuper pattern on the surface of your red blood cells. That's the glycocalyx at work. The proteins, meanwhile, are the true workhorses. They're doing everything. They act as channels, letting specific things in and out. They are receptors, catching signals from hormones floating by. They act like cellular glue, holding cells together to form tissues. Some of them are even enzymes, speeding up chemical reactions right there on the cell's doorstep. They are absolutely the powerhouse of the membrane. Section 4. A balancing act. Now, we've thrown this word fluidity around a few times, but let's really put it under the microscope. This property is all about the membrane's incredible ability to be neither a true liquid nor a true solid, but something perfectly, beautifully in between. So what does fluidity actually mean? It's the ability to be flexible, to bend without breaking, and to let all those proteins and lipids just move around. And this is non-negotiable because a living cell isn't a brick. It has to be able to move, to divide in two, to merge with other things. A rigid wall would make life completely impossible. But a cell doesn't just cross its fingers and hope for the best. Nope, it actively manages its own fluidity. And it has 3 main control dials it can turn to get things just right: the temperature of its environment, how much cholesterol it has packed in there, and the type of fatty acid tails on its lipids. Let's see how these dials work. Temperature is pretty intuitive, right? Heat things up, molecules move faster, and the membrane gets more fluid, more like an oil. Cold does the opposite. It gets stiffer. Cholesterol is fascinating. It acts like a buffer. It wedges itself in there to stop the membrane from getting too fluid when it's hot or too rigid when it's cold. And finally, remember those fatty acid tails? This is where they become a huge deal. Those kinked, unsaturated tails can't pack together tightly, which keeps things nice and fluid. But the straight, saturated tails, they can stack up neatly like logs, making the whole thing much more rigid and stable. And if you want a perfect, real-world example of why this matters, look no further. When a cell needs to ship something out, like a hormone, it packages it into a tiny bubble called a vesicle. That vesicle then travels to the edge of the cell, and what does it do? It seamlessly merges with the outer membrane, spilling its contents outside. That fusion, that beautiful melting together, is only possible because the membrane is fluid. So, Section 5, structure is everything. Let's pull all of this together now. The core principle, the main idea behind this entire biological marvel, is that form dictates function. Every single piece has a shape for a very specific reason. So the next time you picture a cell membrane, please don't just see a bag. See an intelligent, dynamic system. The fact that lipids hate water is what creates the boundary. The specific, complex shapes of the proteins are what create the doors and the communication lines. And those unique sugar patterns of the glycocalyx, that's what creates the ID badge. Every single piece is perfectly designed for its job. Which leads us to one final, really critical question. We've seen just how essential this flexibility is, so think about it. What would happen to a cell if its membrane suddenly lost that balance and became as rigid as a sheet of glass? Well, it couldn't move, it couldn't divide, it couldn't send or receive signals. It would, for all intents and purposes, cease to be alive. That delicate fluidity isn't just a nice-to-have feature, it's the very definition of a living boundary.